Before we look at 7.3, I had a few questions I had gotten emailed regarding 7.2, so let's look at those together. So this is 7.2. So somebody emailed me asking about this question. Which of the objects display self-similarity on different scales? Broccoli, cupcake, coastline fern, or your left foot? Well, we're looking for self-similarity, and we looked at that at broccoli, how a little piece of itself looks like the whole stalk if you zoom in. And we looked at a fern the same way, how one leaf can look like the whole fern on a different scale. The coastline also can look like itself. In 7.2, there's a nice drawing of your coastline of England. So when you zoom in on, when you look at this, it looks all zigzaggedy, but when you zoom in, it again looks all zigzaggedy, and when you zoom in again, it continues to look zigzaggedy. So you can zoom in quite a bit before all of a sudden you see a straight line. In fact, you'd practically be standing on the beach looking at it before you'd see a part that's a straight line. It looks kind of zigzaggy and have this jaggedness at different scales. So that's why the coastline is included in there. So your cupcake, unless your baker's a fractal, is not going to have other little cupcakes in it on a smaller scale. Same thing about your left foot. Not going to have any other little left feet sticking out of your left foot on a smaller and smaller scale. What else did I get asked? So this one we looked at as well. So we're looking at how many triangles it takes to make up the Sierpinski triangle at different stages. So here you have stage 0, and then you shrink that down to half as wide and stack it up, and you make another stage 1 of the Sierpinski triangle, and then you shrink this down to half as wide and put it in the stack of 3. So then you have 9 triangles, and then this gets shrunk down half as big and put in a stack of 3. So now you've taken 9 triangles and put it in 3 different stacks, so that's 3 times 9 or 27 triangles. And then this gets shrunk down half as big and put in a stack, 3 stacks. So 27 in 3 sets, 27 times 3 is 81. Then you have to answer that for the nth stage. Did anybody answer that? Did anybody see the pattern there and answer that? How many triangles at the nth stage? So what are we doing at each stage? What's the pattern?
Multiply by 3.
Good, multiply by 3. So you multiply by 3 each time, and we actually can do that in math, right? When you multiply by 3 over and over again, you use exponents. So for example, 3 squared is 9, and that goes with stage 2. 3 cubed is 27, and that goes with stage 3. 3 to the 4th is 81, and that goes with stage 4. So you can put 3 to the n here. So when you type this in, type 3 raised to the n power. Where did that go? Which one was it? This one? Yeah, so type it like this. You use a little, where did that go? There's a little thing you click on up here, and then from the options, there's a square root option. The notation you need is under the square root option. It showed momentarily there. Okay, so you need this notation, and if you pick this drop-down menu right here, you get a box raised to the box, and that's where you can put your 3 to the n. I don't know why it's not showing anymore. believe there was other questions as well. The Koch curve was the Koch stool was the other one I wanted to show you. So the Koch curve, we took the center piece of a line segment out and replaced it with equal length line segments making a point right here, and we did that in class. And then we shrunk it down to repeat the process. In the Koch stool, instead of putting a point from an equilateral triangle, you put the top part of a square. So all these line segments are equally as long. The next stage would be to shrink this down 1/3 as big and fill in these 5 line segments over and over again on these 5 present line segments. Well, we're not going to have to do that, but it does ask what iteration you're on. And then it depends, like, how do you count? Do you count the line segment as stage 0 or stage 1? And it turns out they're counting the line segment as stage 0. So this Koch stool here is iteration 1. You'll see this Koch stool again in a future Mindscape question. Does anybody have any questions? Okay. Reminder that you have study group tonight. Your quiz 2 is on Monday, so if you could go to study group tonight and on Wednesday and just do the parts that are hard in particular from the review and make sure that you're understanding how to do that. Jake will check your work and tell you if you're doing it correctly or not. In 7.3 then, we're talking about dimensions. So we start with the dimension of a cloud. What would you say the dimension of a cloud is? How about if we recall what we know about dimensions? So what was the smallest dimension that we looked at? Anyone remember?
0.
Yep, 0 dimensions. And what did we draw that was 0 dimensions? A dot, yep, a point. Or 1 dimension was next. And what did we draw for 1 dimension? A line, good. 2 dimensions, what did we draw for that? Square. 3 dimensions, we drew a cube. So these objects fit in their dimension, but we didn't really define dimension. We gave an informal definition of dimension. So let's look at that informal definition again. Does anyone actually remember the definition of the dimension that we gave? Well, one informal definition was the degrees of freedom of movement degrees of freedom of movement. So in 0 dimensions, there is no freedom of movement at all. But in 1 dimension, there's 1 degree of freedom of movement, the horizontal, the way we drew it, horizontal direction. When you have 2 degrees of freedom of movement, then you have 2 dimensions, vertical direction of movement or horizontal. And then in 3 dimensions, there's the vertical and horizontal, and one more that we could call up, or height, width, and depth. Another informal definition we gave was the how many pieces of information to locate a position. How many pieces of information to locate a position? So if you live in 0 dimensions, everyone knows where you're at. There's only one place to be. If you live in 1 dimension, though, you'll need a street address. Okay, so maybe I live at 1, my neighbor lives at 2, and a squirrel lives at 1.5. So you need a street address, 1 piece of information in 1 dimension. Then when we got into 2 dimensions, to locate a place, you needed 2 pieces of information to find a point, horizontal direction and a vertical direction. In 3 dimensions, you would need 3 pieces of information to locate where you're at. And we drew a sketch of how you would try and plot a point in 3D, but we didn't spend much time on it, and we won't today either. Okay, so thinking about your cloud. Back to the question. What dimension is a cloud? What do you think? Could you fit it in a plane? Is it 2 dimensions, so it fits in a plane like in Flatland? No, it kind of sticks out, doesn't it? You put the plane through it and it kind of sticks out. Well, what about 3 dimensions? Is it a cloud 3 dimensions? Good. I always thought it was, but you wouldn't be asking that if it was that easy. Okay, so your marker here is 3 dimensions. Height, width, depth. You could measure it, couldn't you? Could you measure the cloud? Height, width, and depth?
I feel like you could, but it shouldn't be that easy.
Why would I be asking if you could? So like the problem is, where's the edge? Right? Where's the edge of the cloud? It's kind of fuzzy. I mean, it doesn't have substance that you can grasp. So it's a cloud's not quite 3 dimensions because you can't really measure its height, depth, and width. But it's certainly not 2 dimensions because it does have thickness. If you put a plane through it, it sticks out on either side. Well, in fractal dimensions, we have the same kind of problem. Let's look at some of your fractals. Let's look at the Koch curve. So looking at your Koch curve, remember we took this set of 4 line segments and we shrunk it down and then replaced each of the 4 line segments with the reduced copy. And then we shrunk it down again and replaced each of those line segments with the 4 little line segments. And we just kept doing that. So the bottom curve represents the infinite Koch curve in all of its stages. Now, of course, we can't actually draw that. It's limited by the size of the pixels on the paper. But if we could zoom in with the computer, you would just keep seeing more and more and more of the iterations of the Koch curve. So what dimension would the Koch curve be? what do you see? Well, when you drew it, you knew what you were drawing. When you were drawing here, what pieces were you drawing? You were drawing lines, right? You were drawing line segments. So in some senses, it's a line. How long is the line that makes up the curve in its infinite iterations here? How long would that line be?
When it's never ending, since it says infinite iterations.
Yeah. So it'd be never ending, because there's a beginning and an end, but it would go on forever to get to the beginning and end because of the infinite iterations that it has in there. Does it have thickness?
I don't think so, because it's just still a line.
Still a line? It's kind of like mold on a bread, though, in the sense that it's kind of fuzzy, right? Like the line's all curled in on itself over and over if we could see more deeply. So it kind of has a little thickness to it as well. So it is a line in a way, but again, I say curve, but it's actually line segments. Well, we're going to explore dimensions more carefully and get a better definition. We need a better definition so we can talk about, well, what is the definition of this Koch curve and other fractals as well. So to get to that better definition, we're going to take the life lesson for today, which is start with the simple and familiar, and we're going to explore in the simple and familiar. So on our way to looking at dimension more carefully, we're going to take and make copies of simple and familiar objects. We'll start with a square. We're starting with a square because everybody agrees what dimension the square is. 2 dimensions. Now we're going to make a square twice as large. So we'll make a square twice as large. So I made my square one line width wide. So now I'll make a square twice as big. So it's going to be 2 line widths wide. And so here we go, 2 line widths wide. Now how many copies of the first square would I need to make the square that's twice as big? How many copies of the first square are required to make this twice as big square?
4?
4, yeah. So 4 copies. We need 4 copies of the original. Well, let's make a square 3 times as big. So we make a square 3 times as big. Now how many copies of the original would you need to put together to make that square?
12.
12. So it's 3 times as tall. So it's going to be 3 times as tall as this one. And then 3 times as wide. So how many is that then? 9. Okay, 9 copies. Okay, so we're looking in 2D, and we're making bigger copies, because this is going to lead us to our definition of dimension. So we're starting with something familiar. Now we'll do the same thing with a cube. Cube is going to be a little harder. So this was 2D. Now we'll go to 3D. So there's my cube. I'm going to make a cube twice as big. And when I say twice as big, I mean if you took a ruler and measured each side, it would be twice as big. So the height then will be 2 lines tall instead of 1 line tall, and the width would be 2 lines as wide. Now I'm gonna have a little problem, aren't I? Because I drew this too high up. Better lower it, because I'm gonna run into my words. I guess it's easier to erase this part, because I have to show the little depth going on here. Okay. Hopefully you planned ahead and didn't have that problem. So this cube is twice as wide, twice as tall, twice as deep. How many copies do we need of the original? Let's look on the face. Okay, so we did that with the square. We put the 4. So if I just put 4 cubes stacked up, will that be right? No. Why isn't that right?
Because you're not stacking 4 rectangles or 4 rectangle cubes?
Okay. Well, I see what you're saying. Yeah, because they don't go all the way back that far. They only go back this far. Like that, right? Okay.
You need 8 cubes.
So we need 8 cubes. Okay, great. 8 cubes. So we need the stack of 4 in the front, but those aren't thick enough. So we need 2 stacks of 4, and then they'll have height, width, and depth that's twice as much. You know where this is going, right? No, 3 times as large. And this time I'll start a little lower down. So the front face is easy. 3 times as large. In fact, we can copy the front face from our square up above. Okay, so last time how many stacks of 9 cubes do I need this time?
Oh, stacks of 9 cubes.
Yeah, how many stacks of 9 cubes do I need this time?
3 stacks of 9.
3 stacks. Okay, 3 stacks of 9 cubes, because that way it'll be 3 times as deep also. So 3 times as wide, 3 times as tall, and 3 times as deep. Whoops, boy, that didn't work. Okay, this is better. I'm going to do that over. So how many cubes of how many copies of the original did we use?
21 copies.
3 times 7 is 21.
Oh, sorry,
That's okay.
27.
Yeah, 27 copies. Yep. Okay, so 27 copies of the original stacked in a stack of 9, another stack of 9, another stack of 9. And then you have a cube 3 times as large as the original. Well, let's go ahead and take a look at a line. So we'll go back to one dimension now. So here's our original line. Make a line twice as large. So if you make a line twice as large, that's pretty straightforward. You just need two copies. Lay one right after the other, and you have a line twice as large. And to make the line 3 times as large, well, then you just need 3 copies. Three copies of the original. Well, let's go ahead and put all of this information in a chart. So we're going to try to understand the simple things more deeply and see if that leads us to a definition of dimension as we see the differences. So we have the original object. Then the dimension of the object. The original object, the dimension of the object, the scaling factor for the object, so we made objects twice as big or 3 times as big, so our scaling factors will be 2 and 3. And then the number of copies needed to build a larger object. The number of copies needed to build a larger object. So we'll go ahead and make this chart. So we had, let's start with the first dimension. So we started with a line, and that's a 1 dimension. And then we made the line twice as big, and it took 2 copies of the line to make the line twice as big. And then we did that again. We took the line, which is 1 dimension, but this time we made the line 3 times as large, and it took 3 copies of the original line to make the new line. Then we'll take a square. So that's 2 dimensions. And we made it twice as big. When we made the square twice as big, it took 4 copies of the original square. Then we did that again with a square. So the square is 2 dimensions. This time we made the square 3 times as large. And it took 9 copies. That brings us to the cube. So the cube is 3-dimensional. First we made the cube twice as big, so our scaling factor was 2. And to make the cube twice as big, it took 8 copies of the original. And then we took the cube, which is 3 dimensions, and we made it 3 times as big. So to make the cube 3 times as big took 27 copies. So here's our experiment data all put in one place. There's actually a relationship between these numbers. So see who can find the relationship, and when you find the relationship, then we'll verify it by making a square 4 times as big and seeing if that what we suggested worked or not. So stare at these numbers for a while and see if you can figure out what is the relationship. Someone figured it out in the last class, but I'm sure you can too. You can talk to each other if you think you might have it. I thought about having you do this in groups.
I think I have it.
You think you have it? What is it?
Well, I found out that the scaling factor raised to the dimension of the object equals the number of copies.
Good job. Yep, that is what it is. So the scaling factor raised to the dimension gives you the number of copies needed to scale it that large. So let's verify that. So if we take a square 4 times as big, okay, so the scaling factor would be the 4, and the dimension is 2, so we'd have the scaling factor 4 raised to the second dimension, that would be 16. So 16 copies needed. So the scaling factor would be 4, the square is 2 dimensions, and this predicts that we would need 16 copies. So let's just verify that. So we take your original square and we make one 4 times as big, And indeed, it takes 16. Okay, well, we've come up with a way to define dimension then, and this is one way to define dimension. The dimension is the exponent that you raise the scaling factor to that tells you the number of copies that you need. This is the formula that you need on your D2L class activity. Like that. Okay. You can write it with just S and D and N, if you remember what S and D and N are. And that's probably something you'll want on your 3x5 card for your quiz as well. So you could take a picture of that now if you want to. So finally, we have a way to define dimension. And so we're going to take that and use that as a way to find the dimension of the fractals that we've been working with. Let's start with the Koch curve. So your Koch curve, this is a drawing in section 7.2. Your Koch curve in this drawing is 9 centimeters long. The Koch curve has a sense of self-similarity. In other words, part of the Koch curve is similar to the whole thing. What we do when we look for the fractal dimension is we take the largest part, the largest subpart that we can, and see how many copies we need to make that. Well, that was weird. I just touched something I shouldn't have. Okay, yay. All right, so this is 9 centimeters long. When I pick apart of this to say I'm going to make copies of it, to make the larger part, I pick the biggest part I can. So I'm going to pick the 3 centimeter part. I'm not going to pick the 1 centimeter part, even though that is possible to use, because it just makes the math all a little bit harder. So pick the biggest piece you can. So if I take this 3 centimeter piece and I want to use it to make copies, so I'm going to make copies of the 3 centimeter piece. How many copies of this do I need to take and glue together to make the 9 centimeter piece?
4.
Yeah, good. 4. So you take this 3 centimeter piece and you put one here, one here, one here, and one here. So 4 copies. So the number of copies of this 3 centimeter piece that we need is 4. So that's going to be N in our little formula. What is the scaling factor? How much longer did I make it? As measured by your ruler. Yeah. So the scaling factor is how much bigger we're making it. Like the scaling factor for the square, we made a square twice as wide or 3 times as wide. How much wider is this whole 9 centimeter Koch curve compared to the 3 centimeter Koch curve?
3 times.
Yeah, 3 times as wide. So the scaling factor is 3 here. We're going to make this big 9 centimeter Koch curve 3 times as big as the 3 centimeter Koch curve. And to do that, we take 4 copies of the 3 centimeter Koch curve and paste them together. We're actually pasting them on this spot right here, like that. So we could make a real rough drawing for your notes, okay? Let's find the fractal, the dimension of the Koch curve. So we take, this is the roughest drawing ever of the Koch curve, okay? we take this and we make it 3 times as long. So this is the original. And we make it 3 times as big. So the scaling factor is 3. And to do that, though, we actually needed 4 copies, because that's how you get the little point in the middle. So you lay one of these small copies here, one here, one here, one here. 4 copies put together the Cope curve. And then we use our little formula. So S raised to the D equals N. 3 raised to the D equals 4. Well, that's not easy to solve. I mean, that's not an integer answer. 3 to the 1 is 3. 3 to the 2 is 9. So the dimension of the Cope curve falls somewhere between 1 dimension and 2 dimension, just like we might have expected. It has more dimension to it than a line, but not 2-dimensional yet. So you'll need a calculator that has this little up arrow button or some way to calculate exponents. And we'll go ahead and figure out the dimension by just guess and check. So we're going to use guess and check. We'll say 3 raised, let's see, we need some number between 1 and 2, so I'll put 1.5. 3 to the 1.5, well, that's much larger than 4. I have to get 3 to the n is 4. So how about 3 raised to the 1.2? Well, that's a little smaller than 4. I'm trying to get a 4 out of this. So 3 raised to the 1.3. Okay, so I need something between 1.2 and 1.3 for my exponent. 3 raised to the 1.25. That's pretty close. About 3 raised to the 1.26. That's very close to 4, isn't it? You should be able to get within 1/100th of 4, or whatever yours is. So you should do guess and check till you can get within 100th, and then it'll be okay. Okay, so I'll say D is 1.26. So the dimension of the Cope curve is about 1.26. Now, you know, mathematicians have ways to find these exact values. There's a little formula here if you like to use it. So we'll say or. Where did I put that formula? Ln of n over ln of s is the dimension. So you can use either one of these formulas. This is kind of nice if you have a calculator that does the natural log, the ln. But this is fine too. We'll go ahead and look at a dimension of another curve. Before we do that, I did want to show you one of the pictures. Your author puts in 7.3 a picture of the platonic solids treated like the Sierpinski triangle. So here, for example, you have the tetrahedron with the center tetrahedron removed. So this tetrahedron is made up of 4 smaller tetrahedrons, which in turn are made up of 4 smaller tetrahedrons with space removed. So kind of interesting. Okay, let's take a look at the Sierpinski triangle next. And this is something I would expect you to be able to do on a quiz, okay, to be able to find the dimension of the fractals that we've been looking at. So we're using the formula S, scaling factor raised to dimension equals number of copies needed. You can write out as much of that as you want or just use the initials. here's the Sierpinski triangle. So this Sierpinski triangle is 12 centimeters long. I'm going to have to measure on the edge. I can't get the ruler on the screen. Well, look at that. It's not 12 centimeters tall. Pretend this is perfect. It's 12 centimeters wide. So something must have happened in the printing process. It's supposed to be 12 centimeters on each side. So 12 centimeters. Okay. So you can pick any of these triangles and make copies of it, because the whole Sierpinski triangle is in each thing, in each of the triangles. But we want the largest portion of this that we can use and make copies of, just to facilitate the math. So what's the biggest subtriangle that I can pick out here? How big is it?
6 centimeters.
Yeah, 6 centimeters. So the biggest one you can pick out is like this one, or the one on the top, or this one. Okay. So you're going to pick out this big one. I'll just take this one on the lower left. How many copies of this 6 centimeter how many copies of this 6 centimeter triangle do I need to put together to make the full 12 centimeter Sierpinski triangle? Anybody? This is empty. There's nothing here. Okay.
Would it just be 3 ones?
Yeah, so it's just 3. So you take this big one, make 2 more photocopies, and paste them on, and you make 3 copies. So 3 copies are needed. So that's the number of copies is 3, n is 3. What's the scaling factor? And make the big one from it. How much bigger is the big one for the scaling factor? So you're measuring its length now.
Twice?
Yeah, so it was 6 centimeters, and now its new length is 12 centimeters, twice as long. So scaling factor is 2. We're going from 6 centimeters to 12 centimeters, and we need 3 copies to do that. So S was the scaling factor 2, and N is 3. So we have 2 raised to the dimension of the Sierpinski triangle equals 3. So we know the dimension is bigger than 1, because 2 to the 1 is 2. But the dimension is not 2, because 2 to the second power is 4. So this again falls between the dimension of 1 and 2. It's thicker. There's more substance to it than a line, but it's not really quite a solid 2-dimensional figure. So 2 raised to the, I'll just try 1.5 first of all. That's not too far from 3. Let's try 1.6. That's a little bigger than 3. So I need something between 1.5 and 1.6 for the dimension. 2 raised to the 1.55. How about 2 raised to the 1.58? How about 2 raised to the 1.59? Okay, so I'm going to pick 2 raised to the 1.59 because that's 1/100th away. This is very close also, right? That's 11 1/1000ths. I'll pick 2 raised to the 1.59. So the dimension of the Sierpinski triangle is 1.59. So now we have a formal definition of dimension, and we are able to find the dimensions of the fractals, which are falling in between dimensions, in between the integer dimensions. We'll look at the Sierpinski carpet on Wednesday, because that's as far as we got in my first class. Also, you'll need a deck of cards on Wednesday. I emailed you a reminder. I'll see you on Wednesday.
Well, I didn't know who she was, so I had to ask.